Swayam Prabha. Digital India. Educated India.
Welcome to the second lecture in automatic facial expression recognition as part of the Affective Computing lecture series. So friends, in the last lecture, we discussed about the components of a typical automatic facial expression recognition pipeline. We also talked about the different variations with respect to the type of data. You can have static facial expressions, that is only one frame, or you can have your dynamic facial expression where you have a series of frames coming in. Further, we also talked about the types of expressions, essentially which tell you the label. You can have your macro labels, which are your universal expressions, your angry, disgust, happiness, sadness, and surprise, and so forth. And you can have micro expressions, the twitch of the eye, the subtle movement of the lip corner. Now, these are involuntary movements, but these are extremely important for understanding the affective state, the emotional state of a person. Then we talked about the facial action coding system, where you have the action units, different parts of the muscles coming together to create a smile, to create an expression of surprise for this side. Right? Now, what you see here on the slide is your typical pipeline of a facial expression recognition system. You have the object detection, where frames come in, you get the face, you get the facial landmarks. And then, as we discussed the last time, we are interested in extracting useful, meaningful features, statistics around the facial region, the facial parts. So we're going to now deep dive into the facial expression features and see how these features are extracted, how they have been proposed in the past 20 odd years, and what can be their advantage and disadvantages. So we're going to start with the most simplest of a feature. Okay. So let's say here I have a face. Now in this frame, I draw a smiley. All right. So assume that this is your face. Now what I can do is I again detect the face using a object detector, and then I find out the location of the parts, which are the landmark locations. Now once I have these landmark locations, so I'm just pinpointing them here around the facial parts, I can extract what is referred to as geometric features. Now, as the name suggests, we are interested in extracting the facial geometry, and this facial geometry is a factor of the facial points which you would be extracting using an object detector. Now, clearly, at least for macro expressions, there is a strong relationship between the facial component and the feature way of construction. Okay, so when you use these geometric features, you can understand if a person is smiling or is a person sad, because the facial points are moving as such. Now, in one of the very interesting works, Gimmer and Lee in 2013, they proposed that you can have two types of geometric features. One is based on the position, where is the tip of my nose, and the other is the angle. So when I smile and you notice my face, so the angle between the outer corner of the lip and the lower center of the lip. Now you use the angle and the position, and you can have different number of facial landmark points, and you can create analysis of the expression based on the angle here and the Euclidean distance. Right? Now this will be a feature. If, for example, in a face, the distance between the points here on the upper part of the lip and the lower part of the lip is high, so let's say this is D1, then if it is greater than another value D2, which of course for the same face you are getting from a neutral expression, so this distance, then you can say, well, this is where the mouth is open, so the chances are the person could be showing, for example, a surprise or a happy expression, right? Now, notice in this work, the authors had 52 facial landmark points. You can have a larger number of points as well. And these points are based on the type of object detector which you are going to use. It is noticed that shape or geometric features by themselves are not always sufficient. The reason is as follows. You're trying to analyze the expression of a person, and the person, let's say, gives a smirk. Notice my face, right? I gave a smirk. Now this smirk, if you have lesser number of points, will not be appropriately captured by the landmarks points. Another example is when you have action unit 6 and action unit 7 coming together, then you see the narrowing of the eye aperture, right? If you have lesser number of facial points, then the geometric feature will have insufficient information. Therefore, in a large number of applications, we use a combination of not just geometric features, but also feature extracted from appearance or texture. Now, when you will add appearance or texture, that is going to help you in discriminating these scenarios. For example, where you have AU6, action unit 6, which is present, but action unit 7 is not present, right? And that is going to give you wrinkles for the eye corners, right? That is very vital information. Now, friends, let's talk a bit about the appearance textures. Now, appearance means essentially the skin component of your face, right? So we would like to have a texture feature descriptor which can analyze the different parts of a face such that you can have the information about the change in the skin when a facial muscle moves. Now, there are a large number of approaches which have been proposed in the literature for expression-based features when you're analyzing the appearance. Okay. The simplest base is, well, given a face, you can extract the pixel intensity values. Okay. Now, what that will mean is, let's say here you have a frame, you create a face here. Okay. You are going to analyze each and every pixel in your face, and then let's say create a representation based on the pixel information. So you can create a histogram, for example. Okay, you say I'm going to create a histogram which is going to have the range, let's say it's 0 to 255 is the intensity range. So you are going to create n number of bins, so 0 to 15 for example, then you go from 16 to 31 till similar to 255, and you scan all the pixels and you keep on adding here. Okay, keep on adding here, you increase the frequency, right? Now that is another feature descriptor based on pixels. Now a big limitation of pixel based appearance analysis is the weakness of pixel intensities to the change in illumination. So when the lighting condition changes, the pixel intensity changes, and that means, let's say when in image 1, same expression was there, and then you had image 2 captured after a while with the subject showing the same expression but in a different lighting, then the histogram which you would create based on the intensity, that will be different. Now histogram here, notice they are from the same facial expression of the same person but are different because the lighting condition has changed. Another issue is when you have effects such as translation. Now what that means, in frame 1 you had your face, this is your frame 1, and in frame 2 the same person moved a bit, let's say by a few pixels. Now the expression remained the same. Now since you are having this intensity based features, some new information will be added here, some information might go out. We will not have always the same feature representation. If you were to then divide the face into patches, right, local regions, you wanted to compare region by region so that you have in detail and comparison of the facial regions, let's say feature from here to feature from here, the translation will have an effect here. Therefore, in literature it was proposed that let us use orientation based, gradient based information. Now, it has been shown that our eyes are also sensitive to change in the shape. Now, similarly, for analyzing the change in the shape, which is reminiscent to the facial expression, you can use the gradient information. Okay. Researchers have used the standard Gabor filters, the Gabor wavelet filters, to look at the different orientations, the different changes in the facial expression when you apply different filters, and then they will do, let's say, a histogram based representation or similar representation. Or the more popular ones, for example, the histogram of oriented gradients and the scale invariant feature transform. Now let's discuss these two. Okay. Now your histogram of gradient for facial expression analysis will be as follows. So you have a face which is detected using an object detector. What you do is you divide the face into non-overlapping blocks. Okay. For example, here I am dividing. Now further, what I am going to do is I am going to compute the edge map, so that what I get is the gradient. When I compute the change in x direction and y direction, I get information for the gradient. Now what I'll do is I'll create a histogram of gradient for each block here. Okay, this is block 1, so let's say you get h1. Now you append that with the histogram which you get from the second block, and you then do it for, let's say, if there were n blocks. Now there are some post-processing operations which are done to increase the robustness of this feature to illumination. Okay. For example, normalizing it based on the variance and mean. Now this feature is an extremely powerful feature, which when you'll give to your machine learning algorithm should be able to differentiate the macro expressions and micro expressions as well. The other one, friends, which is extremely popular, is your scale invariant feature transform. Now this was proposed by Professor Lowe in the early 2000s. Now scale invariant feature transform based facial expression recognition would mean here you have a face. Now you run the SIFT facial point detector, which is essentially the interest point detector proposed for SIFT. What that will give you is these points. Now these points are the important points where there is change happening in the texture in all the directions. Now once you get these SIFT points, very similar to how you did for your histogram of gradients, you will take the region around a point. Let's say I got this interest point, so this is the region around this point. Okay, this is the eye region. You will create a histogram and this histogram will encode local information, so small histograms coming together based on the orientations again, right? So you can either use your HOG or SIFT or variants of these, and then you can learn again a machine learning system. Now it has been shown in a large number of studies that these appearance features, they perform much better in terms of classification accuracy as compared to your geometric features. Of course, one can do fusion as well, that is, you have an appearance feature and a geometric feature, and you then combine them before you learn a machine learning classifier. Now, for geometric features, the advantage is that they are extremely fast in computation. So low complexity, so they have low time complexity, and also they have low storage requirement, because all what you are doing is you have some facial points, and on the basis of that you are doing some comparisons, for example computing the distance between facial points or computing the angles. Now compared to this, the descriptors from appearance, they have higher computational complexity because you are analyzing pixel by pixel, so they are generally slower to compute, higher time complexity, and they have higher storage requirement. Therefore, depending on the type of application which you want to develop, where facial expression is going to be extracted, you can choose geometric, appearance, or a combination of both. Now, a very simple example which I would like to share, friends, is, let's say you want to create a simple app in your phone which analyzes the images which are taken from a camera, and then based on the facial expressions, it clubs the images together. Okay, so you join images together based on facial expressions, and you can say, well, I have a feature in my app which can show the most happiest moments of a particular event. Okay, so in that case, if the faces are clear and closer to the camera, that means they have a large face size in the images, what can one do is you can have an object detector, and then you can extract the facial points, and for things such as happy, your geometric features could be good enough. To increase the performance a bit more for, let's say, those expressions which are not captured by the geometric feature, one can have a histogram of gradient where you have less number of blocks so as to have less time complexity. What this also means, friends, is when you were extracting appearance feature based on hog, you were actually doing a global feature extraction for the face. When you were using your SIFT, you were first getting the points, the important interest points on the face, and around each interest point you were extracting a histogram, which means we will have what is referred to as local features extracted. Now, an obvious question arises. If given a face, I have n interest points. Around each interest point, I compute an appearance feature descriptor based on SIFT. For each image now, I will have n SIFT feature descriptors. How do I learn a classifier? Because typically, what you will have is each data point is represented by a histogram. But when you are doing SIFT, you have a large number of histograms. Therefore, when you have this kind of situation, typically we have these pooling methods which are used for expression recognition. And I'll give you a quick example of one. So, a simplest one is called your bag of words. Now, this concept is coming from the language domain. What you are saying is, well, I have n histograms which are around n locations in my face. Let each histogram be one word and each face be a bag. What I will do is I will create a pooling mechanism so that these n histograms, they can be created and compressed into one histogram, which I can further use to do training. Now quickly, how do we do that? Let's first erase ink on the slide, what you are saying is I will create a bag or a dictionary. So I will take all the train samples, and let's say I have m train samples, basically m faces, and I may have n interest points. So I will have n into m data points. I'll do clustering and get what is referred to as representative clusters. Now what that should mean, let's say in your faces, you have a set of smiling faces, sad faces, neutral faces. You extract these interest points, you do clustering. So you have your points, you created these clusters. Maybe cluster 1 corresponds to a smile, cluster 2 corresponds to a frown. So now you have these representative clusters. What you will do is you will take one sample at a time. So you take one data point which contains n interest points, and you will create a histogram by looking at the frequency of occurrence of representative clusters in a face. You compute the distance between the shift histogram for each point with all the features of clusters, and you assign to the nearest neighbor, and that will give you the histogram. Now this solves a lot of problems. Not only, friends, now I can have a method for n different facial points for a face, but if instead of a face, a single frame, I was given a video, if I was given a video, then as well I can do pooling using bag of words, right? So you have frame 1, you have frame 2, you ran your object detector, you got the face, you got the landmark points, and let's say you extracted global or local features, right? So what you will do is you will create a dictionary using, let's say, clustering. So you could say, well, one representation is one frame is a word, and this is represented by, let's say, a hog based feature. You do dictionary based clustering, then you do the histogram process creation, which is essentially referred to as your vector quantization. Now you will have a single histogram for one video. Okay, so this could be a face across all the frames, and this way you can have facial expression recognition for dynamic, where you have a series of frames coming in. Now we also have another way of extracting motion features. See, when I say you can create a bag of words based representation for a video that is going to analyze each frame as a word, I'm not learning the relationship between each sequential frame. You started smiling, right? The onset, apex, offset. So every frame, frame 1, has a relation with frame 2. Therefore, an ideal feature representation should be the one which not only looks at the spatial information. For example, when you apply hog to a frame, you extract spatial information, but also looks at the time series, right? The changes which are happening across time, because facial expressions are dynamic in nature. Therefore, motion based features are extensively used. In a work by Ambardar and others, they showed that when you add motion based information into your features, you can do better facial expression recognition. There are a large number of methods. Let's look at the most prominent and commonly used ones. So the first one is optical flow. So optical flow is a traditional computer vision based technique where you say, well, given a series of frames, I want to know where my pixel from frame 1 moved to in frame 2. In context of your faces, that will mean you had smile starting in second frame, you had the same face, and let's say smile increasing a bit. Now this frame at the corner, this pixel at the corner, that has moved a bit in the next frame, right? So what is that flow, which is the velocity and the direction in which a pixel has moved? So once I compute this optical flow, then I can have different type of pooling methods, again similar to bag of words. So friends, what happens is you have n frames, let's say as input, you will get n minus 1 optical flow frames, which tells you, how a pixel is moving from first frame to other frame. Now you can extract any feature. You can say, well, I want to do a histogram of gradient again to each optical flow based frame, and then a bag of words, and then classify. So now what is happening? We took the face as an input, we extracted the flow, it told me how are the points moving across time, and then we looked at the change in spatial domain as well. So each optical flow frame now has a histogram representing the orientations of the gradients. You can do some pooling because you have a video, Bag of words is one. One could say I want to go even more simpler because I don't want to spend more computation cycles, right? So I could say, well, then just compute the max, min, and let's say average across all the hog frames. You get 3 frames, you can flatten them, and then that is your feature vector. Friends, the other one is motion history image. This is a bit older one as well, and it has been used more for human action recognition and has been shown to be useful for facial expressions as well. What you are saying is, I want to create one single image from a series of frames, and these frames are going to be flattened into one frame wherein I'm going to look at the change which has happened in a particular location. So essentially, this one single image is going to contain the history of motion of the pixel across that location. The other one, which is extremely popular and very effective for dynamic facial expression recognition, is your local binary pattern. Now, Zhao and Patikanan proposed this method in 2007, and let's see what this method is. So friends, what you are saying is you have a series of frames again, okay, of a single person. So we are assuming always we have a single person. Now what you do is you would take one block of the frame here, and similarly same size block in the same location, but now in the second frame. So from this volume you would extract a subvolume. So all these non-overlapping first blocks. What you will do next is you will compute the local binary pattern. What that local binary pattern says in its simplest form. Let's say I am right now analyzing the location of the tip of the eye. So this is the outer tip of the eye, okay. You will take one pixel, so this pixel, and what you do is you compare this pixel with its local neighbor. So this is the pixel, this is the tip of the eye. You'll compare this with the neighboring intensities. Now let's say the intensity here, if that is larger than my neighbor, then I would say this is a 1. Now I compare the intensity of this pixel with this one. If this was, let's say, less, I will say it's a 0. So now if it's larger, it's a 1. If it's smaller than the neighbor, it's a 0. This way I will get a 8-bit code. Okay. Now you compute the decimal point for this. Let's say 55, just as an example, friends. And then you will create a histogram of all the points, right? You have created these binary codes for all the points. Now this should give you one histogram. Okay. Now this is taking care of the spatial part. Now Zhao and Petkinen said, well, that's for the spatial part. Now let's do something for the temporal part as well. So what I'm going to do is, let's say I take again this non-overlapping block, first block of my first frame, then I take for the second and third frame, and I have this sub-volume. Okay, so I'm going to draw this sub-volume. So this is X, this is Y, this is T. They said, well, let's divide the volume into 3 orthogonal planes. Okay. What that means is, let's say I have this frame here, which is your xt. Then I have your frame here in the center, which is your xy. And here I have a frame, which is your yt. So you have 3 frames. From each, you compute one LBP. And then you combine this, and this is now your spatiotemporal analysis of the video using a local binary pattern representation. Local binary pattern is also used for texture analysis in computer vision. What that means in context of faces is, for applications such as micro expressions, these have been observed to be fairly discriminative, because you are analyzing the pattern in the texture pixel by pixel and are encoding the difference of that pixel with its local neighborhood in both space and time. So once you have any of these features, friends, you will then learn again the classifier, the same drill we have been discussing about. Now, these are some of the methods for your features which we are going to extract. Another important aspect here is the data, right? Affective computing is a data-driven area. So let's look at some of the facial expression recognition databases which are extremely popular in the community and have very different purposes, which helps us in solving different problems. So we have the Cohen-Kanade data set from the Robotic Institutes at CMU, where you have CK data set and then later, the CK plus data set, which was collected in 2010. And what this data set has is, it has video sequences where a person was asked to come and sit in front of the camera. Now, if you observe me, guys, I'm looking right into the camera, and the person was asked to smile. Then the person was asked to show sad expression. Now, if you notice, what has happened is my head did not move, but the expression changed, right? Now, researchers wanted to have pure expression movement in these samples, and that is how you get these points, data points, where you have the video where the expression is changing. Further, there are over 100 subjects. There is a diverse age range. Notice this is actually not containing much older subjects. This is mainly, graduate students and faculty around the campus. Now, CK and CK plus dataset have been the main breadwinners with respect to the datasets which are used for learning. Clearly, they have added to much progress in the area. But as I explained to you, the method with which the data has been recorded, that means that the expressions are not spontaneous, right? So that brings us to the discussion of what is spontaneous and what is posed expression, right? Posed is you looked into the camera and then you smiled. Spontaneous is, let's say you were having a conversation, you were watching a movie, there was a joke, you really appreciated, you liked the joke, and then you smiled, right? So that's spontaneous. In the real world, we have more spontaneous expressions, but certainly you have pose as well. It's similarly, you can say you have a group of friends who are now posing in front of the camera and they are saying cheese, right? When you say cheese, it's a posed expression, right? Now, mainly these are posed expressions in the case of the cone granite data set. Another aspect to notice, we discussed that in the case of static facial expression recognition, we are mainly looking at the peak expression. So researchers here also labeled the peak expression, which in other words means the expression's highest intensity, which is the apex. Okay. Now researchers moved on from this and then they started looking at different aspects with respect to the recording environment, with respect to the age range, the cultural variability, and also the labels, right? In the case of your CK data set, you had the compound emotions and the universal emotions and the facial action coding system, FACS, action unit labeling. Another work from Ohio State University in 2014 proposed a data set for compound emotions. They said, well, universal emotions are too less, right? And they are not universal as well. We have finer states in between. So, for example, you have surprise and you have disgust. Right? These are two different expressions in the case of universal emotions. You could have a scenario where you could have a person who is disgusted and surprised, right? So the emotion in terms of the expression, that is compounding. So Martinez and others, they proposed this data set containing 5,000 odd images from 230 subjects and had 22 categories of basic and compound emotions, which means now from the perspective of facial expression recognition system, you have a 22 class problem. And that means you can have more fine-grained information about the state of the user. Then friends, we also have the DISFA dataset from the University of Denver. So it stands for the Denver Intensity of Spontaneous Facial Action Datasets. Now, as the name suggests, this is spontaneous. That means the users were shown, let's say, a series of videos, could have positive emotion or negative emotions, and the expectation is that some emotion will be induced in the viewer and that will be shown in terms of facial expressions, right? So spontaneous expressions, and then there was human labeling for facial actions. So you have now 3D data at a high resolution and different ethnicities as well, right? So there's another type of variability which is coming in this data set. Now, all the examples which I have been talking till now have been about 2D data, but we also have 3-dimensional data, friends, right? So you can have a 3-dimension data, either it can be captured from 2 cameras, or it could be 3D data which is synthetic, right? So Lejeune and others, they proposed a data set called the Binghamton University 3D facial expression data set, which samples are shown here. So what you have here is the texture and the shape, right? And this again was created in a bit different manner, okay? So they use a 3D face scanner and then they captured the faces of the participants. In the next version, they actually captured 3D videos, right? Now, when you capture 3D videos, again, one is posed, and then you can go to the next step, which they did, wherein they showed the videos stimuli to participants, and then they got 3D videos, and then they got spontaneous 3D facial expressions. Now, this is one of the works which I was involved in very early on in my PhD 10 years ago. So the data sets which you have seen till now, they have been focusing on facial expressions, posed or spontaneous, but the assumption is that the subject, the user, is always inside the laboratory with good illumination and mostly facing the camera, so looking into the camera as right now I am doing. But this is not how exactly always the data will be when you capture the world around you. Many a times you will see that the pose of the person, that is the head with respect to the camera, would be non-frontal. For example, I am looking towards my left right now. In this case, the camera will only be capturing the right hand side of my face. So we have to introduce these kind of data such that the methods can be tested for these real world conditions. Now, along with the pose, there are other aspects to real world conditions as well. For example, there is occlusion, there is presence of multiple subjects, there is presence of missing data as well. Now, to progress work in this area, we proposed a data set called acted facial expressions in the wild. Now, in the wild here, friend, means this is representative of real world conditions. Now, what we did was, we chose popular movies which had method actors. Okay, now method actors are these high quality actors who would generally show expressions which are closer to spontaneous expressions. But since we are getting data from movies, the environment in which the people are, that is very varied, right? Now, what we did was, we said, well, we would get these movie data, but we need a method to extract those short video segments where a person or a group of persons are showing the expression, right? Could be happy, sad, and angry, and so forth. So what did we do? We extracted closed caption subtitles. Now friends, closed caption subtitles are those subtitles which you would have generally observed when you watch these foreign materials which is dubbed into, let's say, another language and has square brackets around it. Now these words, for example, here you see laugh, these generally will convey the emotion or something which is in the scene, and these are for people with hearing impairment. So we did this simple analysis of the text and we chose those segments which had keywords related to affect and emotion, and then gave us this kind of data which was later either label corrected, because you can always say that the word is related more to happy or not to sad, and then use that label. And along with this, we also had the context. Now the context is as follows: who is the person, what is the age, and what is the gender. Now we can use this information for facial expression recognition training and have more accurate prediction for, let's say, a better model which predicts facial expression for older population, a more accurate model for facial expression prediction in children, right? So this brings us to the end of this lecture. We have discussed the process of feature extraction. We started with the features for frames, geometric features, then we moved on to appearance-based features, and then spatiotemporal features. And later we discussed the different facial expression data sets and their attributes. For example, recorded in lab or recorded outside, posed expression or spontaneous expression, and then the different aspects such as was a 2D camera used or a 3D scanner was used. Thank you.